Hey there, welcome back everyone. We are in part 2 of section 2.5. We've just learned about the correlation coefficient, which measures the strength and direction of a linear between two quantitative variables. The notation is R for a sample and rho for a population. All right, so let's look at an exercise here. Is there really an association between the rate at which a cricket chirps and the temperature? Data was collected. You can see your textbook, example 2.35 if you'd like. If we wish to predict the temperature by counting cricket chirps, it would be nice if the correlation were strong. The scatter plot is shown. Based on the scatter plot, how would you describe the direction, form, and strength of the relationship? So remember, direction is either positive or negative. A positive relationship, as the explanatory variable, in this case chirps per minute, goes up, the temperature would go up. Well, that is exactly what we are looking at here, right? The higher the value of chirps per minute, the higher the observed temperature. So we would say positive. The form, I would say, is pretty linear. If I draw a line through these dots, that seems to describe the relationship pretty well. So I would say it's linear. And the strength, I would say, is extremely strong. Remember what strength means. Strength is measuring how far are the dots in general from the line. Well, these dots are very close to the line. The direction is positive. The form is linear. The strength is extremely strong. Okay, so before we talk about what the value of the correlation might be in this problem, let's talk some facts here about correlation. And when we say correlation, we mean the correlation coefficient. So the correlation is the correlation coefficient, which is a number. So the correlation is always between -1 and +1. The correlation has no units associated with it. If R is close to -1 or +1, then the linear relationship between variables is extremely strong. If R is close to 0, then we say there is no significant linear relationship. And the correlation between variables x and y is actually going to be equal to the correlation between y and x. So it doesn't matter which variable you assign the horizontal axis and which one's the vertical. It will not change the value of the correlation if you switch them around. But as I mentioned at the end of the first video, you must have looked at the scatter plot first and verified it looks linear before you calculate the correlation. Otherwise, the value of the correlation can be very misleading if you don't see what the data looks like. We'll look at some examples that maybe illustrate this. All right, so here's another exercise. We're looking at used car prices. It says you're interested in buying a used Subaru Forester, which is actually spelled like this, Subaru. You do some research on Craigslist and find the following Subarus listed, along with their miles and age in years, and their listed price. So this data was collected in 2012 in the San Francisco Bay Area. As you see to the right, we have the scatter plot of the data. We have years on the horizontal axis. The vertical axis is price in dollars. Okay, so there's our data, there's our scatter plot. It says, using the plot on the previous page, describe the strength, direction, and form of the association between age and price of a used Forester. What's the direction here? I'm going to just draw a line that I think kind of best fits the data. Something like this. That line seems to do a pretty good job at describing the trend of the data, right? As the years increase, the price goes down, right? And we probably could have guessed that before we did this problem. We know that as a car gets older, its value goes down in general. And that is what the scatter plot is showing. And it looks somewhat linear. Now, what about the strength? Well, it's not as strong as the cricket temperature data on the previous page, but this is still relatively strong. And you're going to get a sense of what strong is as you see more of these. But this is still strong. So the relationship is strong. The linear relationship is strong. The direction is negative, and the form is linear. So I'm not going to say I wouldn't say it's extremely strong, but that is, we're going to see as we see more of these plots that is pretty strong. Do you think the linear model is appropriate? That just means, does it seem like the data is linear in form? We've already answered that. Now they want us to estimate the value of the correlation. Remember, if R is close to -1 or +1, then the linear relationship between variables, I should say variables, is extremely strong. It's not going to be -1. -1 would be a perfect line. That's if all the dots would be exactly on a line. But it's also not 0. That's like no significant linear relationship. So I'm actually going to say that this is actually a lot closer to -1 than to 0. I'm going to say it's probably about 0.9. Now it says use technology to find the correlation. So what we do, we upload the Subaru data that's posted on Canvas. We're gonna upload that to StatKey and see that correlation. So here I'm going to upload this data. We go to StatKey. All right, so you can see on the screen here, we have the price and the age of the Subaru. And the correlation turned out to be negative 0.925. So close to my guess, but even stronger than I thought. Right, so just take a look at that scatter plot. While it's not as strong as we saw with the crickets, this is still very strong. We still consider this to be very strong linear relationship between the explanatory and the response variable. So again, you'll get as you see more scatter plots, you'll get better at kind of estimating these values. Okay, so we're back to our basketball example. Which is the best guess at the correlation? So before we get into this too far, let's read number 2. Which of the values listed are impossible for a correlation? So even without looking back at our basketball data, I can tell you that -20 and -2, +2 and +20, those are not possible. Right, we were told that the correlation is between -1 and +1. Now, let's look back at the data now for the rest of it. Generally, a negative trend, right? Not extremely strong, but there's a negative trend there. So let's see what else we can knock out here from our list. We're knocking out 0 because 0 is no relationship. There's definitely a relationship there. And we also said that it's a negative relationship. So I'm going to take out all the positive values. I'm also going to take out -1 because -1 is a perfect linear negative relationship. It's definitely not perfect. And I'm also going to take out -0.9 because that's too strong. So what's left? This is a best guess, -0.4. So you want to see what -0.4 looks like? Take a look at this. This is what we would call, so quite a bit weaker than our crickets. This is extremely strong, and here this is strong. This is a strong negative relationship here for the Subarus. Are there any outliers in the scatter plot? The outliers are values that don't seem to fit the trend, right? I'd say the only value that really noticeably does not fit the trend is this person here. This is a person who got a lot of rebounds, but also shot very high from the free throw line. So that is an unusual player that can do both of those things. So we'd say maybe this person's maybe 1150 here and maybe 85% from the free throw line. So I would call this person an outlier. They don't follow the trend. Here are a couple correlation cautions. Correlations can be heavily affected by outliers. We always plot our data. R equals 0 means no linear association. It does not mean there's no association. So variables could still be related otherwise. So just remember that R value doesn't tell you about association in general, only linear association. And of course, correlation or association does not imply causation. Even if the relationship is really strong between your explanatory and response variable, it doesn't mean the explanatory variable is causing the response variable. To answer that, you always have to ask what kind of study was done. Only experiments can show causation. Okay, so that's it for section 2.5. I'll see you in the first video for 2.6.